So 3 urns contain color balls as follows. Suppose an urn is chosen at random and a ball is withdrawn. It happens to be red. What is the probability that it came from urn 2? In other words, we're trying to calculate the conditional probability of urn 2 being selected given that the ball chosen was red. Now, by definition, if we just tried to calculate this directly, we need to find the probability of the ball being red and coming from urn 2 divided by the probability that the ball would be red. Now the idea here is that we're going to use a bunch of formulas to replace these two quantities. Now first, in the numerator, I'm going to use the general multiplication rule. Now the general multiplication rule can be written two ways. I could write it as the probability of urn 2 given the ball's red times the probability of red. Now I wouldn't want to use that because that would just be, in the end, the probability of R would cancel with that, and I would just get the conditional probability of urn 2 given red is equal to the conditional probability of urn 2 given red. So that's pretty not helpful. So what we always do in the numerator here is we use the general multiplication rule that flips the conditioning on the problem. So if I started with the probability of urn 2 given red, in the numerator, I'm going to write the probability of red given urn 2 times the probability of U2. Now, I'm going to use some new terminology. U2, this is a hypothesis. All right? I have 3 hypotheses here. The ball came from either urn 1, urn 2, or urn 3. Note that these 3 hypotheses are all disjoint. Any one ball cannot come from multiple urns. And they're also exhaustive in the sense that there are no balls that could be chosen that wouldn't come from one of those 3 urns. So I have what I would call now a prior probability that the ball came from urn 2. Now what is that going to be? That's going to be 1/3. Because if I had no information, I would just look at the problem and state, well, there's 3 urns, I'm choosing one at random and then picking a ball out. So in that case, all 3 urns are equally likely. Can I use the classical approach of probability and say, well, 1 out of 3? That would be my prior probability. My goal here is to now update this probability, turn it into a conditional probability by making use of the knowledge that the ball happened to be red. So this is my prior probability. Now what's this quantity here that's also in the numerator? That's a probability of getting a red ball given you've picked urn 2. So this is the likelihood of seeing a red ball, or if I want to generalize this, the red ball is evidence. All right, so this is the likelihood of obtaining the evidence we have given this hypothesis was true. So the probability of getting a red ball given that urn 2 was picked. So that's all in the numerator there. I'm going to replace it with this product over here. Now in the denominator, what's the probability that a ball is red? Well, what we're going to do here is use something called the law of total probability. This picture over here, the circle represents all the sample points that correspond to red balls being selected. Now the idea here is that the 3 hypotheses are disjoint and exhaustive, so they break the sample space up into these 3 mutually exclusive regions. So the probability of event R can be thought of as being the sum of 3 different probabilities. The probability that the ball was red and came from urn 1, plus the probability that the ball is red and came from urn 2, plus the probability that the ball is red and came from urn 3. I can add those together because each of those intersections are disjoint or mutually exclusive. So when I have probabilities of disjoint sets or events, I can sum them up. Now, I don't know any of these probabilities, so once again, I break out the general multiplication rule. So instead of trying to calculate the probability of the ball being red and coming from urn 1, I write it as a likelihood of getting this evidence given hypothesis 1 would be have occurred times the probability of hypothesis 1. Right? The probability of a red ball given urn 1 was picked times the probability that urn 1 is picked. Now for the probability of R intersect U2, I have once again this same setup. The probability of the ball is red given urn 2 is picked times the probability of urn 2. Notice that's the exact same thing that's up here in my numerator. Finally, R intersect U3, I use another application of the general multiplication rule. So what I have here is I've taken the definition of conditional probability and replaced the two quantities with, in this problem, 1, 2, 3, 4 applications of the general multiplication rule. Now, why is this useful? Because when I plug them all in, I can calculate all these numbers. All these prior probabilities, sorry, that should be a U3 there, not an R3. All these prior probabilities are 1/3 because I am just randomly selecting one of the three urns. And these likelihoods of obtaining the evidence that, in this case, a red ball, given that a particular urn was picked, each of those numbers come directly from this chart. If urn 1 is picked, there's a 3 out of 8 probability you pick a red one. If urn 2 is selected, you got a 1 out of 6 likelihood. If urn 3 is selected, you have 4 out of 9. So that's where these probabilities come from down here. Now when you plug them all in, you get 12 over 71, or approximately 0.169. We'll call this a post probability. The idea is we start off with a prior probability, which in this problem was 1/3. Each urn was equally likely to be chosen. But given knowledge that the ball chosen is red, my post probability is 0.169. Now, we have to make sure we understand that this probability here really is a subjective probability. Because once the ball is chosen, right, we got a red ball. Well, it is either a 0% chance it came from urn 2 or a 100% chance it came from urn 2. Because it either did or didn't. However, we don't know that. So the idea here is we're taking our prior probability, using conditional probability rules and the general multiplication rule and this law of total probability, using all these formulas to come up with a new kind of adjusted probability that now measures our degree of belief. Now, why should my degree of belief that it was urn 2 be lower than what it was before the evidence was selected, before we got a red ball? Well, if you go back up here and look at the totals, note that out of the 8 red balls, there's only one of them in urn 2. So if urn 2 is picked, there's a 1 out of 6 chance that you pick a red one, versus urn 1 has a 3 out of 8 chance, and urn 3 has a 4 out of 9 chance. So urn 2 actually has the least likelihood of getting a red ball, given that that urn was selected. And so that's why we see that our post probability is lower than our prior probability. Now, what are the other post probabilities? Like if I asked what is the conditional probability that it was urn 3 given that it was red and urn 1 given that it was red? Well, notice that urn 3 has the largest likelihood of getting a red ball given that that urn was selected. So both of these would increase from a 33% chance. I don't know what they exactly are. I'd have to go through and do all the calculations. But since this guy decreased by so much, the other two would both increase. Now, instead of doing this for every problem, we could have gone and done this using a tree diagram. It would have been very complicated. But there is, since this is such a standard approach where we break it down using the general multiplication rule, this is really known by another name, and that is Bayes' theorem or Bayes' rule. All right, so this is really an application of Bayes' rule.